Okay, guys, today is our third lecture in this series. That is on compression members. And you have studied the basic concepts in the previous lectures related to compression members. You have studied the Euler equation, you have studied squash equation, and you had studied the critical load under which a column would buckle, and you also studied something about mode of failures of columns, and two major modes of failure for columns were material failure and geometric failure. So you can watch the previous lecture to recall some of the basic concepts. Okay, today's numerical is based on a compression member, but this compression member is a built-up member. And built-up members are members or section that are built on demand. Sometimes the sections that are available in industry, for example, C section, channel, or for example, W sections, they are inadequate and they don't fulfill your demand. So we can actually assemble two or three sections to meet our demand. For example, we can fabricate a section that comprises of a channel and a W section. So this would be a built-up member. Similarly, you can join some supplementary plates, gusset plates, to a W section, for example here and here. Now this would be a section of a column, and it would be adequate in the demand that is required. And you should know that column section is used like this. I mean, this is the length. Okay, and when sections are built up like this, the properties of the section would definitely change. So in this question, we are given a built-up member. It consists of a W section, which is W18 into 65, and a plate on its top. You should know that in a W section, this is a flange, this is web or stem. Okay, and this is our plate, and the plate is only attached to top flange, and bottom flange there is no plate. So we have to find the capacity of this column. You should know that this column, if you draw the isometric view, it would be like this, and the length of the column, which is 15 foot, is like this. I mean, it's in the Z direction. If it's X, if it's Y, then this is Z. Okay, clear. The prime aim of this question is that the ultimate goal is to find these design load. I mean, the capacity of your column. So that would be found out by that would be found out uh, in LRFD as well as AST. So for LRFD, I would be multiplying it with 0.9, that is resistance factor, and for AST, I would be dividing it by a factor of safety, that is 1.67. So that's easy. But before that, I have to find the nominal capacity, and for nominal capacity, you have to find this F critical, and you would be multiplying it with the gross area. Now gross area in this case would be the summation of area of this W section and that plate that is attached to it. So it's easy. I mean, F critical, you should know that in a column, a steel column, a steel of a column may not reach its Fy. Sometimes it may fail prior to Fy due to residual stresses. So this would be our material failure. So that's why F critical is modified based on geometric failure and a material failure. So I have used this equation. Now, if you recall this equation is related to geometric failure. And how? I mean, you had to decide whether to use this equation or this equation. It is related to material failure. Sorry, it is related to material failure. For geometric failure, we use this equation, and you should remember from the previous lectures. And you should know that the mode of failure was decided based on slenderness ratio. You had to find the slenderness ratio and you had to compare it with lambda r. This is the lambda r. So if your KL by R comes out to be greater than this critical value lambda r somewhere here, if you are here, then you are going to use this Euler equation. And this is F critical 0.877 F. And if your KL by R, that is slenderness ratio, was less than lambda r, you would be here. And in that case, you had to use squash equation. And the squash equation is this one. So all comes to slenderness ratio and this critical factor lambda r, this boundary limit, and this is the value of lambda r is found out using this formula, whereas E is the modulus of elasticity, Fy is yield, and F4.71 is the factor. So it's easy. So the thing is, the basic thing is, I mean, the prime aim of this question is to find the nominal capacity, and then based on that nominal capacity, you had to find the design capacity. But first of all, FCR. So FCR was found out using this formula. And before that, I had to find the slenderness ratio. I'm using the reverse approach to make you understand the question. It means that I have to find the slenderness ratio of this built-up section. And slenderness ratio of this built-up section would be KL by R. So I have the L value. K would be 1 because if it's not given, then K can be assumed to be 1. The problem is this, and I have to take the R minimum. You know, for for any area, we have two value of R, Rx and Ry, and Rx would be equal to second moment of area in x direction divided by area. Area is same for both, and for Ry would be Iy divided by area of built-up section. It means I have to select the minimum of these two, but I have to find these two values. Now I have the area. Area is very simple to find, but the problem is this, Ix and Iy. If it was a single section, single W section, it was very easy. From the manual, I could have found the Ix value and Iy value, but a plate has been attached here. It means Ix and Iy has been changed. The thing is, I have to find this Ix, Iy. Based on Ix and Iy, I have to find Rx and Ry. And then I have to select the minimum of these two to find the slenderness ratio of this column. Okay, so let's start. So we have this built-up member, and built-up member is W section with a plate attached, and it's W1865. From the manual, I will be going and I'll be finding some properties, and you should know that this is the depth, this depth, W18, and it's not exactly 18, it's 18.34 inches from the manual. 65 is the weight, that is pound per feet. 50 ksi is the yield of steel, it may be 992, length is 15 feet. So now in the next step, I'll go to manual and I'll be finding the properties here, the properties of W1865. These can be easily calculated or easily found out from the manual. Ixx, Iyy, area, and its depth. So let me go back. I'll find the value. Okay, you can see the manual, and 18 W18 into 65. The area is this 19.1. Its depth in inches is 18.4. There it was 18.34 inches. It means it's an updated manual, so it doesn't matter. Then I have Ix and Iyy values as well. Ixx and Iyy. This I and this I. This is moment of inertia, second moment of area along x-axis. This is the second moment of area along y-axis, and this is 1865, and this is 1070, and the other value is 54.8. So from the manual you can easily find the properties of W section. So I have found out the values of W section, the important parameters of W section, and I have written there in the data. The problem is that a plate has been attached with this. The Ix and Iyy and Ixx have been changed because of this plate. So I have to find, this is the Ixx and Iyy of this W section. But I have to find the Ixx and Iyy, or simply Ix or Iy of a built-up section. So I mean the concept is very easy, but you have to calculate the Ix and Iy values. Okay, let me give you some very basic concepts, and you should be all ears to me because this is very important. Okay, we have a W section, and there's a plate here, and let me change the pen here so it's blue. Okay, you should know, if I draw a y-axis here, for example this is y-axis and this is y-axis, okay, you should know that along the left of this line, this y-axis, I have got half plate and half W section, exactly half. Similarly, along the right side of this y-axis, I have half plate and half W section. It means there is symmetry along y-axis. This is, I mean, it is a symmetrical section along y-axis. It means its x dash would be simply the half of this length, half of this flange length. So it's very easy to find. This x, the flange width BF can be found out from the manual as well. Let me go back to manual. For example, I have the manual, and I'll be going to find BF. This is thickness of that flange, and BF, the width of flange. And the width of flange is 7.59. 7.59 inches. Again, thing is, I have this W section, and this is my built-up section. This is a W section with a plate attached at the top, and this is your y-axis. You should know that, for example, this y-axis, this is already drawn. Half plate here on the left, and half W section. Similarly, half plate and half W section. It means there is a symmetry along y-axis. It means x dash would be simply BF divided by 2. What is BF? This, which is 7.59 divided by 2. So as there is symmetry along y-axis, Iyy is very easy to find. Very easy to find. I have found out here, for example, this. So what I did, you have this plate. This is your W section. Let me go here. Okay, the Iyy, okay, just tell me, if you have a plate like this, and you should know, I mean the given is 3 by 8 inches, its width is 3 by 8 inches, depth is 3 by 8 inches, and this is 4 inches. If you have to find its moment of inertia along y-axis, what would it would be? You should know that Ix is BD cubed by 12, but Iy, I have to find the Iy. It would be equal to dB cubed by 12, and d would be equal to 3 by 8 inches. 3 by 8 inches. This is 4 inches. You should know this is 4 inches divided by 12. So Iy of a plate would be equal to this, and you can see here. So I have just take the summation of Iy of plate and Iy of W section. Why? Just summation, because there is a symmetry along y-axis. If there was no symmetry along y-axis, I could not have simply added them up. And you know the Iy of plate is 54.8. So I of built up section along y-axis would be simply equal to this Iyy of a W section, which is given 54.8 plus dB cube by 12. The d is, this is your plate. This is Iy of W section. This is Iy of plate. This is d. This is b. And b is given as 4 inches here. And this is 3 by 8 inches. So 54.8 plus d is 3 by 8 inches multiplied by 4 cube divided by 12. So you'll find some value, and it comes out to be 56.80 inch to the power 4, because it's second moment of area. So why I have simply added them up, and I haven't used this very famous formula BD cube by 12 or IXX plus AD square, because there is symmetry along y-axis. The symmetry along y-axis has simplified the problem. The symmetry along y-axis has simply simplified the problem. A plate is attached, this is y, and you should know that to the left is half plate, to the left is half W section, to the right is half plate and half W section. So that's why there is symmetry along y-axis. So I've just added them up. But what if I have to find I along x-axis? Now this is not simple. So this is my section and this is x, and you should know that on the above this x-axis I have got half W section, okay, and below this x-axis I have half W section, it's okay again. So there is symmetry, but there's a problem. Above x-axis there's a full plate, so there's no symmetry. However, in case of y-axis there was symmetry. Here there is no symmetry. That's why this y dash cannot be half of this. So I have to find this y dash. So I have to use some major basic formula which you have been studying since your second year. And if you have to find the neutral axis along y dash, you should know that x dash is the neutral axis along x-axis, y dash is the neutral axis along y-axis. So the simple formula, very famous formula for finding neutral axis is this: a1 y1 plus a2 y2 plus a3 y3. This is your neutral axis along y-axis. So I'll be using this formula to find the neutral axis along y-axis, this y dash, because I have to find this ixx. So you should be very clear that when you were finding iy, you first found out x dash, and when you are finding ix, you have to find the y dash. So this is very important. So this was very easy to find out because there was symmetry along y-axis. This is not easy to find out because there is no symmetry along x-axis. So let me use this formula: a y dash, area of W section, y of W section, area of plate, y of plate. These are centroid. Yp is the centroid of plate, yw is the centroid of W section, y dash is the neutral axis of whole built up section, and A is the entire area of built up section that comprise of W section and plate. This is area of W section, this is area of plate. So it's very easy and very conceptual. So I'll be using this formula: area of entire section multiplied by neutral axis along y-axis, because I have to find Ix, area of W section, centroid of W section, area of plate, centroid of plate. So I have this area. It's very easy to find out. This area is very easy to find out because area of this entire section would be equal to what would be the area of plate? 3 by 8 inches multiplied by 4 plus the area of this is given from the manual 19.10. So I'll be using this as my area. Y dash is yet to be found out. Area of W section is given 19.10. In order to find YW, I have to select one of fiber. So I have selected this top fiber. And I have to find the centroid from top. So you know that this depth is 18.34 inches. This depth is 18.34 inches. So from the top fiber, the centroid of this W section would be equal to whole width of this plate plus half of 18.34. It's very easy, and you should recall your basic knowledge of PSC. I'm going into detail, but I should not, because okay. So the thing is, I have this 18.34 inches. The problem is I have to find this centroid. So I have selected this top fiber. So how would I find out this YW? So YW would be equal to half of 18, because this is 18.34, this is 18.34. So 18.34 divided by 2, because this entire length is 18.34. So I'll get this 18.34 divided by 2 plus this plate, because I have selected the top fiber. Now width of this is 3 by 8 inches. So this would be YW value. So this, I've done this. I've tabulated it. 18.34 divided by 2 plus 3 by 8. Area of W section is, now this comes out, or that can be placed here easily. Okay, so if you multiply these two, you will get 182.40. These two have been multiplied to get you 182.40. Okay, the plate again in the next case. Let me erase all things. Now, again that section, that is built up section. I have selected this top fiber, and the centroid of this plate would be lying somewhere here, YP. What would be the centroid of this plate? YP would be simply equal to, because you have selected the top fiber, so you have to find all distances from the top fiber. All distances from the top fiber. The centroid of this W section was found out from the top fiber. In this case, I have to find the centroid of this plate from the top fiber. That would be equal to 3 by 8 divided by 2. Simply. Area of plate is 1.5. How? 4 into 3 by 8 gives us 1.5. So if you multiply these two, you will get this. So this would be summation. The formula comes out to be very simple. A y and dash is equal to a1 y1 a2 y2, or simply aw yw, or ap yp, and this is your ay dash. So y dash would be equal to aw yw ap, a area of plate, y of plate divided by a. So it has been done here. I have found this value to be this 182.62, and I have divided by area, that is 20.60. You should remember you should note that this is the summation of two area of plate and area of W section. This is very easy. That it has been tabulated. AY for plate has come out. It's very easy. I don't know why I have to make you understand each and every bit, but let me. Okay, area of W and Y of W, and area of plate and Y of plate. Area, you have the area 20.60. This is this. You have multiplied this area with this. So this is 182.40. APYP, this is this. Now found out. You can easily find out. Y dash, it comes out to be 8.86 inches. It means the neutral axis lies, as all calculations have been made from the top fiber, the neutral axis lies somewhere here, 8.86 inches equal to Y dash. It has been shown here. Okay, so the thing is, I have just calculated the neutral axis, but I haven't calculated yet this Ix. So let me find the, now you should know, it should be noted that I of x of this built up section would be equal to Ix of plate or W section first, and Ix of plate. So I have splitted it here. First I have found the Ix of W section, and then I have found the Ix of plate. But the formula to be used for each of them would be this. This is very famous formula, and you should know this is second moment of area. This is area of that W section, and D is actually the distance between centroid and neutral axis. It seems difficult, but it's very easy. So first, to find the Ix of W section, I have to insert values here. So in the first case, I have Ix of W section. It is there, very much there. Let me clear all the things here. Ix is there. This is very simple, straightforward. 1070. That's why it's 1070 here. Area of W section is 19.1. It's here. And you should know why we are using this formula, Ix plus AD square, because there was no symmetry along x-axis. There was no symmetry along x-axis. However, there was symmetry along y-axis, so I just simply added these two without using this AD square formula. Whenever D comes, it means there is lack of symmetry. And this is very basic knowledge, and this is from your second year. Please go to your second year books, open your books, and you should recall how to calculate these moment of inertia. But still, it's my job to teach you again. In the final year, it's unwanted, but in the final year I am teaching you how to calculate the moment of inertia. Okay, thing is, D is the distance between centroid and neutral axis. So the centroid of this W section was found out to be 9.5 9.55 inches. Now difference between centroid and neutral axis. You should remember, while calculating y dash, I selected the top fiber and I calculated the centroid of W section, and that was 9.55 inches here. However, however, the neutral axis of the entire built up section was found out to be 8.86 inches. 8.86 inches here. So D would be simply the difference between 9.55 inches and 8.86 inches. That is YP minus Y dash. It has been done here. So I have found Ix of W section to be this. Next, I have to find the Ix of plate. So I'll be using the same formula. Again and again I am recalling, reiterating, as there is no symmetry along x-axis. On its above I have half W section and full plate, and below this axis I have got half W section. There is lack of symmetry. That's why I'm using this formula. So, and neutral axis has been changed, Y dash. In case of Y axis, I had got one plate, to the left of this Y axis and to the right of Y axis, both are mirror images and there is symmetry. So X dash is very simple to find out, and you will be adding this simply, but you cannot do it for Ixx. So Ix of this plate would be simply equal to, you will be using this formula, but Ix would be equal to, you should know, if this is B and this is D, no, BD cubed by 12 Ix. It has been done here. B 4 inches, D 0.375, 3 by 8 is always 0.375, plus this AD square, area is 1.5. It's very easy. You multiply 3 by 8 into 4, you will get this area. The only problem is this, and it's very simple. You should know what D is. D is the difference between neutral axis and centroid. So recall, this is your plate and this is your W section, and you had selected this top fiber and you had found out this YP, and this YP was equal to this. This is YP, and the Y dash or neutral axis of entire section was 8.86 inches. So what would be D? D would be equal to Y dash minus YP, as it is square, D square. So it never matters if you if you write it as YP minus Y dash or Y dash minus YP, it does not matter. So Y dash is 8.86 and YP would be equal to simply 3 by 8 divided by 2, or just 0.375 divided by 2. It has been done here. So just solve it and you will get this. And finally, when you are done with it, you have to add these up, this value and this value. My Ix is this, my Iy is this. My requirement is to find the R minimum value, because this is very important point. I'm tired, I don't know, but I have to find this R minimum. R minimum is I by A. In this case, I have finding Ixx and finding Iyy. The minimum is Iy. So R minimum would be governed by this Iy. Why I have to find this Iy? Why I have to find this R minimum? Because slenderness ratio is KL by R. So if R is minimum, slender ratio would be high, and you would be defining for critical thing. I mean, higher critical value leads to failure, higher slenderness ratio leads to failure, or it would buckle. So R minimum would always govern this slenderness ratio. So R minimum would be depending upon Ix and Iy, and the minimum is 56.80, and it's very easy. Its length k is 1. I've multiplied it with 12 to convert it into inches, and this r is uh, from 1.661. So for every built up section you have to find the ixx and iyy. Finally, this is, and you should know this basic, and again this is very important. This is your lambda 4.71 E by Fy. It comes out to be 113 in our case. And our slenderness ratio is 109. So we are here. We are here. We are here in elastic buckling. I have to use this formula. I have to use the Squash equation. It means this. We are here. It's 109 and it's 113 and it's a material failure. So I'll be using this formula. F critical would be this one. Fe is easy to find. Pi square E divided by this have been found out, 109, 29,000 KSI. Nothing is difficult here. Finally, this multiplied 0.9, it's for LFT, and this is for AST. I think it's very easy. The basic problem is this one, this calculating these things and calculating this. So I think I have made a I've made an effort to make you understand. I hope you will understand. If a problem and this is very important, just let me tell you, I mean, you have to understand it. Please listen to watch this lecture again and again, and inshallah you would be able to learn this. You can also practice some questions from the Segway book, and maybe I'll give you some assignments on that. Before midterm, the assignments were mostly theoretical based, but after midterm, there might be some assignments on these numericals. Thank you very much.